want to mention propositional logic, even though it is not enough to prove that a program is working correctly, it does give you some insight into how automated theorem proving works. Very simple one, but it is still an example of how that works. So is that okay? All right. Because before, the interest of propositional logic is kind of more of a research, kind of more of a theoretical side. But these days, we actually have a pragmatic reason why this becomes important. All right. So given that context, what we want to do is to introduce general propositional logic, also known as propositional calculus. So a propositional logic system is a four tuple. Okay, I think this is the funny looking L lambda, and it has four parts. Each part is a set by itself. So we have alpha, omega, zeta, and iota. Okay, so except for this one, you can say A, Z, and I. I really don't care which way you say or which one you pronounce it, but it's alpha, omega, zeta, and iota. So there are four sets. Each set serves a different purpose, so we'll start with alpha. So alpha has a set of symbols to be used, and symbols have no inherent meanings. So all they are is just symbols. But there are three categories of symbols. Okay, so this is where having Joplin can be handy. Let me go start up Joplin. And by the way, I fixed the audio, and I've started to record. Yep, go ahead.
Would you say that first, the L-looking symbol,
I think that's lambda.
lambda?
Yeah.
And so does that represent like a function you're utilizing, or not a function,
Um. Nope. It's just a funny looking L, but I'm guessing it is lambda. No, it is collectively. This entire thing. It's just basically giving a name to the four tuple. Yep. It's propositional calculus depending on these four sets, and each one serves a different purpose. All right, so I am going to start up Joplin because I want to kind of write some notes in class, and once again, I can share that at the end of the class. So if somebody is to remind me to share that, I can do that. All right, so I'm gonna open a new one for this class. Note. Okay, there we go. Just gonna stash it over here. And then get rid of those two so I can 2024 oh no, today's October 7th. There we go. All right, so we'll start with alpha. Okay. So alpha is a set of symbols, but there are three different kinds of symbols. So the first kind is constants. Okay, they always cannot have the values changed. So that would be, as an example, 0, 1 are constants. But 0 really does not necessarily have to mean false, and 1 does not necessarily have to mean true. They are really just symbols. But they cannot have different values. Okay? So whatever meaning 0 has to say the same for the entire system. Whatever meaning 1 has to say the same for the entire thing. The next one are variables. Okay? So variables can have any constant values. So that's why they're called variables. So typically we use English letters for that purpose. So basically letters from the English alphabet, P, Q, R, S, T, and so on. So these are representing things can either be a 1 or a 0 because the 0, 1 are the constants, and variables can have any one of those particular values. So are we doing okay so far? Can we distinguish between what a constant is from what a variable is? Okay, so because those two are pretty much the same as what we normally use in programming, so they're not a problem. The next one is a little bit harder. They're called schematas. Okay, so a schemate, I guess, schemata is one. Okay, So these are typically Greek letters, something like theta, rho, um, phi, psi, and so on. And I guess rho, I did not spell rho correctly. What is rho?
There's an H and then
RHO? Yep, you're correct. There we go. So schematas are different. A schemata is a wild card, but it's not, I cannot talk about the context of how the wild card is going to be used. So for now, we'll just say that these are wild cards. Okay, wild cards to be substituted by something else. I know it sounds awfully vague, okay, but at this point, because we are only talking about the symbols, I cannot explain what a schemata is because I cannot quite explain the context in which they are going to be used.
Can you just say special characters?
They're wild cards, okay? They're basically things that can take on um, entire expressions, okay? So if a variable can take on a particular constant value, then the schemata can take on an entire expression. But I cannot talk about expressions yet because we need the next set in order to talk about expressions. So so keep just just don't try to read too much into schemata yet. All right. So the next set, okay, so we're going back to set here. The next one is omega, but this is big uppercase omega is a set of what we call operators, which are also called connectives. So you go like, what exactly is an operator or connective? Easy, okay? Things that we already know, okay? So I'll just give you some examples here, okay? This is an operator or connective. What does that mean in normal Boolean algebra? It means and, okay? And what? How many operands does it have? In other words, how many values does it need in order to quote unquote operate? Two, that is correct because it's an infix notation, so it needs two operands. Okay, so we have a bunch of these things. Okay, this is another one needs two operands. Okay, let's fix the spelling here. Let's do something that only requires one, okay, which is the negation symbol. This one needs only one operand, okay, and so on. So the ones that require two operands, is in a subset of omega called omega 2, okay? So basically, in terms of notation, so we can say omega subscript 2 is a subset of omega um, consisting of operators that need two operands. And by that token, omega 1 is a subset of omega consisting of, there's only one here, an operator that need one operand. Is that okay? That's just the notation. Okay, that's all it is. It's just a notation. So if you want to invent a different system where you define your own strange operator that requires three or four or five operands, that's fine. Okay, you can have omega 4, omega 5, and so on. But basically, omega is a set of what we call connectives or operators. Are we doing okay so far with all this stuff? Okay, are we good? Yep.
So just to make sure, for any given connected, the subscript will define how many operands it needs.
Um, yes. So in this case, okay, so typically, okay, so when we talk about an example, so typically we want omega to only have the operators that we are familiar with. So that would be, just conjunction, disjunction, negation, typically those three are the ones that we want in the entire omega. But the system, okay, so when I describe the entire system, you don't have, this is an example, okay, this is a typical use of propositional logic. But if you want to go like, but I want to invent my own propositional system, you can do so. You can introduce operators that require more than two operands. Okay, but I'm just so one is a general thing, and then the other one is kind of more of a typically when we are working with propositional logic, that's what we use. Okay, so are we okay so far? Between alpha and omega. So let me go back to the discussion of alpha because I just want to give you an example of typically what do we want to include in the alpha. So we have the two constants 0, 1. We typically have a bunch of um, letters from the English alphabet, all lowercase. So P, Q, R, S, T. And then we have some Greek symbols. I typically use psi a lot, also a little phi, and also rho. Okay, if you want to include theta, that's fine. Okay, and so on. Are we doing okay so far? All right. So now we can define the next section here defines what is a WFF. It's not WTF, it is WFF, which stands for well formed formula. Okay, so what exactly is a well formed formula? So let's just take into consideration our example at this point. Okay, everything in alpha is automatically a well-formed formula. In other words, 0 by itself is well-formed. P by itself is well-formed. Q by itself is well-formed. Okay, so that's just definition. That's how we start the definition of what is a well-formed formula. Okay, so I'll just start to type here. Okay, every element of alpha is is a well-formed formula. By themselves, they're not terribly useful, but we have to start somewhere. Okay. So once we have that in our example, any operator, any expression with an operator and the right number of operands is also well-formed. Is that okay? So let me just explain that. Okay. Every expression using an operator and the right number of operands is also a well-formed formula. So I can give you a few examples here. Okay. For instance, 0 and 1, okay, is a well-formed formula. Is that okay? Well, let's check out why it is well-formed. If you look up, this wedge symbol, which is it needs two operands, are we providing two operands in this expression? Okay. Is each one of the operand also well formed by itself? Well, 0 is well formed, 1 is well formed, so 0 and 1 is a well formed formula. Okay, is that okay? All right. So I can give you another example. Okay, so let's say we have another one which is P and Q or R. Okay, that is also a well formed formula. But this time we have to kind of do a deeper analysis. So let's take a look at each letter first. Is P a WFF? Is Q a WFF? According to how we define alpha. Okay. Is R a WFF? Okay. All right. So then the next question is recursively define your well-formed formula. Is Q or R well-formed? Okay, so what do you think? Is you think about the OR, okay? Where is it coming from? It's coming from omega 2 because it has two operands. So now you look at the two sides of the OR and you ask, does this OR operator have well-formed formulae as its components? Yes. Q is well-formed, R is well-formed, so Q or R is well-formed. Is that okay? So finally, we look at the end, and then we look at on the left-hand side first. Okay, P is in the well-formed formula. Okay, Okay, what about the other side, which is by itself an expression? Well, we just established that it is also well formed. So, from the conjunction perspective, it is also well formed because one, okay, let me point here, because one, it requires two things. Are we supplying two things? Yes. Each one of those two things well formed? Yes. P is well formed because it is from alpha, and then on the other side, Q or R is also well formed. Is that okay?
Can you say there's not well formed if you don't have the parentheses?
Hmm?
Can you say there's not well formed if you take away the parentheses?
It would still be well formed here because in that case we'll just have to depend on operator priority to figure out which one to perform first.
Why would it make it not well formed?
Oh, I can make a lot of examples of not well formed because we just have to break the rules. Okay, remember this is the mindset of a hacker, right? How do we break the rules? So we can now say, what about P negate Y? P negate Q. This is not well formed. Okay, so let me scroll up here. Is not a well formed formula. We can have even more examples. Okay, so let's say we have just a single wedge. Oh, okay, wedge P is not a well-formed formula because what happened to the other side of the wedge? Is that okay? So anytime you supply the wrong number of operands to a connective or operator, it is not well-formed. And anything that makes use of at least one component that is not well-formed is automatically also not well-formed. Okay, so the well-formed formula is basically just syntactically what can we generate out of alpha and omega. Is that okay? So let me just write it here. Okay, I'm gonna de-indent two twice. There we go. So the space of WFF or well-formed formulae is all the syntactically correct expressions. Some may not be useful at all. Okay? For instance, I can give you an example. Okay? Uh, this is well formed, right? So now this is well formed as well. If that is well formed, okay, then this is also going to be well formed. I can nest this, indefinitely, but from your perspective, it's good. Like, okay, tag, you get the point. Okay, false is false, false and false is false, false and false is false, false and false is also false, and I can keep going like this indefinitely. I can create an expression that will fill up the entire screen, made out of just nested versions of the same thing. Is that meaningful? No, it is not meaningful. But is it syntactically correct? Yes. Okay? So well-formed formula has nothing to do with is it meaningful? How are we going to interpret this? Nope. It is just asking, is it syntactically correct? In other words, will it compile? Is that okay? All right. So with these two already discussed, the next one is called iota. So iota is important. Okay. Yep.
Okay, so that's the Z symbol.
Hmm?
That's the Z symbol in your propositional logic.
No, this is iota is the I.
Oh, but the last one was.
The last one is iota. Yep, I think so.
Or okay, well, is WFF going in place of the big Z?
So the big Z is the next one. We'll talk about that last.
Oh, that's iota. Wait,
Yeah. No, that's transformation. The set of transformations.
Okay. Okay.
Yep. But I need to talk about iota first because we need a starting point for the transformations.
Sure.
Yep. Go ahead.
So how does WFF fall into the four parts of that of proposition and logic? Does it fall within that, or is that just like a general?
Sort of. So how many people have taken linear algebra? Okay, if we're taking out linear algebra, A is kind of like the vectors, okay, and then omega is kind of like how you can span a space using vectors. So the space, which is not which is not spelled out here, is how you apply the operators to the alphabet, to the symbols.
So it's technically part of omega.
It's not part of omega, it is how you use omega to combine with the alpha in order to generate a space. A space in this case is not spatial, it's not like a two-dimensional space. It is simply talking I'm simply talking about a set that contains all the well-formed formulae. So I call that a space.
Omega are the operands that you can apply to the alpha.
To the alpha and other expressions in the well-formed formula space. Okay? So we do it okay so far? So everything that is syntactically correct can be generated between alpha and omega. Because the only syntax, the only rule that we have talked about up to this point has to do with omega. Each operator has an expected number of operands. So you have to give it the right number of operands, and each operand by itself also need to be well formed in order for the entire expression to be well formed. Is that okay? And to start, because we have to start somewhere, so to start, everything in alpha is automatically well formed. So that's how we can define what is syntactically correct, and there's an infinite number of syntactically correct expressions. Is that okay? So now, in order to talk about iota, I have to basically say, okay, so when you're trying to prove a theorem, okay, how do you start with proving a theorem?
You have to make a supposition.
A supposition, but okay, so the teacher who's asking you to prove a theorem have to give you something to start with, right? Some kind of, like, okay, we know this is true, this is true, this is true, and this is true. Can you prove that that thing is also true over there? Is that correct? Yep, go ahead.
Like axioms or
Um,
postulates?
Axioms refer mostly to, okay, so you can have axioms as the rules, but you can also have quote unquote axiomatic truth, which is basically, just, what is true and what is not. Is that okay? So I can give you an example in this case, what is true and what is not. Okay, because you can assign meanings to every symbol in alpha. Okay, so I'll go ahead and kind of give you an idea. Okay, so we'll before we talk about iota, let's talk about um, what variables can potentially represent. Okay, so I can give you an example here. Okay, this is going to be a funny example. P is whether, okay, tax classes are super boring. Okay, in other words, that's the meaning, that's the semantic behind the variable p. Now, why is it a variable? Because it may be true, it may be false. Is that okay? So that means, this p is not axiomatically saying that text classes are indeed super boring. It is asking the question: is it true or is it false that text classes are super boring? So that's why it is a variable. Okay. So now I can also say something else. I can say Q is a meaning of is Iraj's classes super boring, or is defined as Iraj's classes are super boring. Okay, is that okay? So these two are variables. So now I can say that axiomatically one thing is always true. Okay, so we can make this funny, and we can say, P or Q is axiomatically true. In other words, I'm not going to tell you whether text classes are boring. I'm not going to tell you whether Iraj classes are boring. I'm just telling you that axiomatically, don't ask me why, okay? That's the truth of this particular universe. P or Q is true, okay? Then you go like, but it doesn't really tell us anything about whose classes are is boring, because there are three possible scenarios. only text classes are boring. Only erogenous classes are boring, but they're both boring, right? But we cannot resolve which one of the three cases, and neither do we have to do that. Is that okay? Are we doing okay so far with variables and what can be axiomatically true? Okay. So once we know what is axiomatically true, then we can now describe iota. Iota is a set of WFFs that are axiomatically true. Don't ask why, they're just true. Is that okay? Now, we can include things that are interesting. Okay, so for instance, okay, this is definitely just an example. So an example of iota in this case is, okay, I am going to say that the symbol, okay, sorry, let me scroll up here. So I can say, okay, I'm just axiomatically saying that the symbol 1 is true. Now, can I define it the other way around and say the 0 is true? Yes, I can, okay? But it would not be consistent with how we normally refer to the symbols, so let's just kind of stick with things that we are making sure that things are consistent. So we want to stay with things, definitions, and keep the consistency. So in this case, I can throw in, oh, the negation of 0 is also axiomatically true, okay? But I can also throw in just P or Q in this case. So in this strange universe, okay, P or Q, as defined earlier, is true. But not P itself, okay? P itself is not axiomatically true. Q is not axiomatically true. We just know that P or Q is axiomatically true.
So all the elements of the set need to be true in
Hmm?
order to be
Say
all the
again?
elements in the set need to be true in order to.
We only put axiomatically true expressions into iota, which means these are not derived from something else. Is that okay? All right. So I can also put in things, like, okay, I can expand, the strange rules of this universe, and I go like R is um, students who are taking tax or Iraj's classes get enough rest, okay, because they sleep in the class, okay. um, so I can now say, let's see, I think that's enough here. Oh, I can do this. So I can now also say P or Q implies uh, R. So that means I need one more operator in my omega. So in my omega, I'm going to include implication. There we go. And scroll back up. Is that okay? So these are just truths of this particular universe, okay? And I'm going to throw in one more thing, okay? Let me see. Okay, we'll throw in not S. I'm not sure whether this is going to work out or not. So S means um, Tom is not getting enough rest. I don't think it's going to work out because I don't have quantifiers in propositional logic. If you want to throw in quantifiers into the whole thing, it is not first order logic anymore. It's going to be called second order logic, which is predicate calculus. It's also in the scope of this class. Hmm. I don't think this is going to work out, but but as an example, is it still okay? I just cannot use the logic part to get it to work. All right. Okay, so that's the story of this universe. Okay, the story of this universe is between tax classes and the rush classes, you know, one category, at least one category, are super boring. Okay, that's just a universal truth. The second universal truth is a little bit more awkward. Okay, because it says if at least one of the two categories of classes are boring, that the students are getting enough rest. Okay, students who are taking my classes or rush classes are getting enough rest because they can sleep in class. Is that okay? And then the third one is Tom, which is a particular person, is not getting enough rest. So those are the universal, those are the axiomatic truths in this universe. Yep.
Negation S is Tom getting enough rest or not getting enough rest?
It is Tom is getting enough rest, I guess, because it's the negation of not getting enough rest. So Tom is getting enough rest. Mhm. Are we doing okay so far? All right. So there's at least one thing I can do. Okay, there's one transformation I can at least do in this case. So now we are ready to talk about what is exactly proving a theorem. So in proving a theorem, you have some axiomatic truths. Okay, so those are the pieces that you start with, and what is the second piece? The actual question. Can you use the axiomatic truths to come to a conclusion that some other expression is also true? Is that kind of how proofs usually work? You have some starting ingredients, and then you have one statement. Typically, you have one statement that you want to connect to the axiomatic truths using logic. Is that okay? So this part is harder for me to describe verbally. It is easier to draw a picture. And is it okay for me to take up one of the screens and use the whiteboard? Okay. I promise you this is not going to be a super complicated diagram. If you need to copy it on your notes, it's easy. So I'm going to pull up the screen and turn that off. There we go. All right. So I'm just going to give you an example. So let's just say that this is the entire space of well-formed formula, of well-formed formulae. So this is the space. So every dot here is representing a well-formed formula, like P and Q, okay? P or Q, not P and Q, and so on and so forth. Is that okay? Um, so now I need several colors for this to work. So where are the, oh, they're usually in the box. I got blue, I got red, that should be fine. Okay. So there are a lot of dots, in this space. Okay, they're all over the place. In fact, there usually is an infinite number of elements within this space. But we're just going to call each blue dot an element in this space. Is that okay? So iota are basically things that are marked as being true. Don't ask me why. They are just true. Is that okay? So I'm going to use the red color to initially circle the ones that are in iota. Okay? So I'm going to circle this one, and circle this one. Okay? Is that okay? So in a mathematical proof, You typically have a few things that are given to you and they are true to begin with. And then the question in the proof is to ask you, can you make a logical connection so that we can also call, okay, I'm going to use a black to circle. Can you also, make a connection to that well-formed formula so that there's a logical connection that if these three are true, then that one has to be true too. So that's typically the format of a mathematical proof. You start with something, and you're trying to make connections to a particular statement because you want to prove that that statement is true as well. Are we still doing okay so
It's
far?
kind of like saying that you have your x and y and you're trying to find out your z.
Not so much you're trying to find. All of these are statements that can be either true or false. Okay, every single blue dot is a well-formed formula, which means it's a Boolean expression that can either be true or false. Every single one of those. But the ones that are circled red are you're told that those are true to begin with. Is that okay? The one that is circled in that's circled in a black circle, that's the one that I want to find out if the ones that are circled in red are true. Can we also prove that the one circled in red is also true? I'm talking about the format of a mathematical proof. You're given certain things that are known to be true, and you're asked to see if there is a connection between those and a specific statement that can either be true or false, but we want to show that it is also true. As a result of the red ones, or the ones circled in red, are true also. Is that okay? All right. So how do we get there? Okay, the way we get there is transformation. Okay, so I'm going to use. Um, Unfortunately, I don't have another color. It would be nice if I can get a different color, but I don't have another color. So I'm going to use like a certain notation here. So transformations allow you to look at the pattern of the ones that are true to begin with. You go like, oh, if this is true and this is true, it fits a certain pattern, and I can now mark that this one is true too. Okay, so um, I'm gonna use blue here. Okay, these are derived. So I can now say if these are true, then this one is gonna be true.
I'll try
Okay,
this.
huh?
I don't know if it works. It's a
The
green.
blue would work too,
I
but
don't know if
you
it
have to
has
remind me to
or not.
retry it.
I don't know
I
if
wonder if it smells differently.
it says right, right?
Just kidding. Okay. So now I can also say, okay, so each transformation rule is a pattern. It is asking, can I find these things with this particular pattern? Oh, yes, I can. Then I fire the rule, and then I can mark something else as being true. So it may be possible that for me to look at this one and this one and say, they meet a certain pattern. So when these two are both true, then I can come to the conclusion that this is also true. So by applying these transformations, hopefully, okay, so I can now say, oh, this one and this one combined can say that this is true. This one alone can imply this one is true, and so on. In other words, I can apply these rules and mark more and more of the blue dots as true. Is that okay? The question is, can I reach the one that is circled in black? That is basically what a mathematical proof is. So if I'm successful, so I'm just using this as an example. So let's just be lazy and say that, oh, these two combined is going to say that that one is also true. Then I have completed my mathematical proof because I started off with things that I do not question because they are given to me as true, and come to the conclusion that the one that I need to prove is also true. So that's the format or the mechanism of a mathematical proof. Are we doing okay so far with this picture? Okay. So you can draw that picture, in your notes. You can just kind of describe it too, because my voice is being recorded, so that part is being recorded. So now, in order to try to specify the transformation, which is how we make these explains here. If these two are true, then this one is true. If these two are true, this one is also going to be true. So now we have to be able to specify the transformation, which is about specifying, patterns. Okay, so I'll give you a pattern. Okay, so I'm going to say here, a transformation has two parts. Um, Here is an example. Okay, so the example is going to look like this. Um, we have a set, and then we have the infer symbol, which is your v dash. Okay, so if you want to use LaTeX, it is called v dash, and then we have another expression here. So I'll be more specific here. So I am going to specify, okay, we'll specify one that is, um, well, we'll specify one that is kind of, it looks trivial to begin with, but it's also kind of, it's awkward. Okay, so we'll talk about this. Theta, I'm going to use psi wedge um, the negation of psi. Okay, and let me scroll up. There we go. So this is a really odd transformation. In other words, what this is doing is, in order for this rule to fire, I have to match psi to one well-formed formula. Does it have to be a well-formed formula that is already known to be true? No, because this empty set says there's nothing I require from the well-formed formulae that are already known to be true. So this particular set on the left-hand side of the infer symbol specifies what needs to be known to be true to begin with. That set being empty means I don't need to know a single thing. Then you go like, then what does how does psi come from? It means your psi can be any well-formed formula. Okay. Oh, really? Just any well-formed formula like P or Q or R or T or S or 0 or 1? The answer is yeah, yeah, any one of those. But it does make sense, right? Because I don't really need to know whether the variable t is true or not. Because between t and the negation of t, one of them has to be true, so the disjunction has to be true. So this is a strange transformation rule where I don't really need to know anything that is true to begin with. I can fire it already, like almost instantaneously. Is that okay? Now there are ones where it is required. Okay, so the next one is also going to be obvious. Okay, well, I think it will sound obvious. Whether it really is obvious or not, we'll take a look. Okay, v dash. Okay, and that's basically just the format of a transformation rule. So this one says, okay, give me two expressions, okay, two well-formed formulae that are known to be true to begin with. The first one is psi, the second one is phi. Okay? And then what I can conclude that has to be also true is the following. You guys would go like, that seems obvious, but maybe it's not. So psi wedge phi. Okay? So that's a well-formed formula that has something that needs to be true first, okay? And if I can find two well-formed formulae, and they are both true to begin with, then I can infer that the conjunction between those two also has to be true. Does that make sense to you? Hmm?
Not necessarily.
Why not? Because
They
if
output.
hmm?
Um,
So these are wildcards, which means they are just matching things, right? So psi is basically saying, okay, I can be used to match anything that is already circled over there. Okay, so anything that's already circled can take the place of psi. It's a placeholder. The same thing applies to phi. So I can go to that picture with all the things that are already circled. I go like, hey, you can be phi. Okay, if two well-formed formulae, okay, they can be the same also, okay. Once I find two well-formed formulae to take the place of psi and phi, then I can find the well-formed formulae that is in this case psi and phi and say, hey, I can circle you now. Does that make sense? It is all about finding things that are already circled that fit a particular pattern, and then find something else that I can also circle. Yes?
What does the B dash stand for?
Infers.
Bird.
Infers. So infers and imply are closely related. Infer is a syntactical transformation, whereas implies is a logical conclusion. So that's how they're different. Yes, go ahead.
Wait, so that psi symbol that has what you just said, that
Mhm.
specifically only defines that.
So it is just a placeholder. When you want to apply a rule, okay, okay, I can give you a slightly different one, okay, so you can, um, so I have to think about it. Mm, Oh, okay, that I can make one that is kind of obscure, okay, not obscure, but it is it's a result of what we already know, okay. So now I can say let's find the negation of psi, but we'll find phi which is not negated. And then we are going to conclude that one more thing. Okay, so we'll find one more thing here. Uh, okay. So don't copy anything yet, because I'm not done editing this. Okay, there we go. Let me double check because I need backslash in front of the side. There we go. Okay, let me double check whether this makes sense or not. Okay, it does make sense. Okay. So in this case, in the third transformation rule, I'm looking at a very specific pattern now. Okay, I'm basically saying I'm looking for a single well-formed formula. Okay, what about that well-formed formula? It has to be an OR. Okay, the last operator to be applied has to be an OR. Okay, and then I have specific requirements of the one on the left-hand side. It has to be the negation of some well-formed formula. So psi is some form of well-formed formula that is first negated, and then the entire negated psi is used in a disjunction. Is that okay? So if I can find something like this, and I can also see that psi as a well-formed formula is also already circled, then I can go ahead and circle phi. So this is where the pattern matching becomes important, because what I'm really looking for are two well-formed formulae. The second well-formed formulae is constrained by the first one, because this is basically saying I need a very specific well-formed formula. Using the diagram, I think it's also easier to explain, because the pattern that I'm looking for has to be the last operator has to be an OR operation. The OR operation has two sides, okay, the left hand side and the right hand side. The left hand side has to be the negated something. So I'm looking for this particular structure of things that are already circled. So I'm applying this pattern and on every single thing that is already circled and ask, hey, are you in this format? No. Okay, fine. Move on to the next one. Are you in this format? Nope. Okay, fine. I'm gonna move on. But as soon as I find one that is labeled, that is structured like this, then I go like, okay, I have a match. So once I have a match, then I know what psi should look like and what phi should look like in that specific case. Okay, but once I know what is psi and what is phi, then I'm gonna also go look for psi by itself as a well-formed formula that is circled. Okay, so I search in the entire space. If I cannot find psi by itself, which is already circled, then I cannot fire this particular rule. But if I can find both of these, like I can find, okay, for example, okay, just as an example, if the circled portion has not P or Q as already circled somehow, okay, and I also have P also already circled, then that particular rule can apply, because P becomes psi, Q becomes phi, okay, and P by itself, which is psi, is also circled. So now these are two are circled. The question is, what about Q? Well, the first thing is Q is in that space because Q by itself is a well-formed formula, so it's in the space anyway. The big question is not whether it is in the space. The big question is, can I circle it? Because I want to circle things. So according to that rule that you see on the projector, if not P or Q is already circled, if P is also already circled for whatever reason, okay, they may be already circled because of being in the iota set or because the result of firing some other rules. I don't know and I don't care, okay. But if I can see that not P or Q is already circled, if I see that P is already circled, I can now go ahead and circle Q and apply. Basically, I apply the transformation rule. Is that part okay? Now you can make stupid ones, okay? So the stupid ones, which are not wrong, but they are not particularly useful. I can give you. Okay, we are almost out of time, but I can do at least do this part here. B dash. Okay. If you see a particular expression psi that is already circled, okay, now I can actually also circle psi and psi. Does that make sense to you? In other words, if I going back to here, if I see that not P or Q is already circled, then I can go ahead and circle not P or Q and not P or Q. Is it particularly useful? No. But can I circle it? Yes. Because this rule is consistent with the normal way that we use Boolean algebra. Okay, so that means I'm not gonna accidentally circle something that I'm not supposed to circle because of the fourth rule here. But is it really useful to find out, to prove a theorem? Probably not. Okay, is that okay so far? All right. So I'm gonna stop the lecture right here, because it's already a lot of concepts to understand, especially the transformation, because the transformation is that okay. I think now you start to see the application of the schemata, right? The schemata are basically the wildcard symbols that are only used when we try to specify a rule, because each Greek letter is used to match an entire well-formed formula. Yes.
So it's essentially safe space. Like when you're writing out, if you have a long thing that you're trying to prove, you can
It's
put it into one of those wild cards and save space when you're writing stuff.
well, it saves space, but it's also a way for me to designate the structure of what I'm looking for, but also be able to refer to the parts of what I'm looking for, of various parts of the structure. Because the nesting of the operands or the operators will give me the structure, but I need something to refer to the individual items, within the expression, so that I can refer to. I also need to find, in this case, on the third rule, it says if I can find this, I also need to find psi by itself circle. So that's how the schemata symbols are used. Basically they are pattern matching variables, so to speak. Each one is not being matched to either true or false or zero or one of the constants. Each one is being matched to an entire well-formed formula. All right, so I'm going to end here, okay? But if you need to remember one thing, it would be the transformation rules are about, how can we circle more things in the space. That's basically what it is about. And hopefully, at some time, at some point, we're gonna be able to circle the one that we are supposed to circle.
It reminds me a lot of this philosophy class I took.
Sorry?
It reminds me a lot of this philosophy class I took.
Which class?
Philosophy 3.